different view because of that silhouette edge. I'm going to load up another data set now. This is a set of CT slices of a sloth. It's 197 slices, each 128 squared, to demonstrate the next set of capability of this program, which is raycasting through the volume data set. So here we have a sloth torso, and I'm going to do just a little slicing into it. Take a look at there you can see the rib cage, the heart, and various other internal organs. Now I'm going to switch to a different rendering mode. Instead of slicing, we're going to go to raycasting. In this case, we have the capability of projecting rays through the data set, in each case perpendicular to the plane of the screen, and so one can project the rays at an arbitrary angle by rotating the object because the rays are fixed perpendicular to the screen. You'll notice that when we rotate in ray tracing mode, we just display the edges of the cube. That's because it's not possible to keep up with raycasting through such a large data set while we're moving it. And in this mode, we have 4 different rendering models that we can use. The first is texture mapping, which is the same model that we use in the slicing mode. The second is density sum. This sends rays through the volume, and along each ray it sums all the values that the ray intersects. And here we can start to see some of the detail of this particular data set. For certain data sets, in particular X-ray crystallography data, electron density data, this is a more valuable technique than others. The next technique is called maximum voxel. Again, we're sending rays through the data set, but this time, instead of summing all the values along the ray, we're selecting the maximum value that the ray intersects and choosing that for the pixel value. Something else you'll notice is that this program uses successive refinement while it is rendering. That is, it does an initial pass at low resolution to see if the view is good, give the user immediate feedback, and as long as the object remains in one location, it continues to refine the image. Here you can see right where the cursor is pointing is where the successive refinement is going on. So you can see above this line it's getting smoother as it renders at a higher resolution, and below this line it continues to be jaggy because of the low resolution pass. One need not work in this mode. You can either select successive refinement off or on. If it's off, it goes immediately to the higher resolution pass. So that's the second form, the third on our shading models. The final shading model is a shaded surface raycasting, where the following has been done. We have selected various ranges of the 8-bit data and identified with them different color and opacity values. So for example, for this particular data set, skin was identified to be between the values 60 and 89. That's on a range of 0 to 255 because it's 8-bit data. It was made fairly transparent and given a particular color with red, green, and blue value. Muscle was the next range of values above 90 and up to 134. Again, was made fairly transparent, slightly more opaque, and a different combination of red, green, and blue values. Bone was said to be everything above 135, was made quite opaque, and given yet another color, in this case very close to white. So here we can see the results of this. First of all, you can see the transparency of the skin. It's not completely transparent, but it is mostly transparent. The opacity of the different bones. Some of the bones seem clipped away here. That's because that is where I sliced into the model. One can slice and then ray trace if one likes, or can ray trace the entire data set. Here you can see this line coming down where the cursor is pointing and doing the successive refinement we talked about earlier. Just to show how easy it is to change parameters in this ray tracing model, I'm going to go into the skin values here and change the opacity to completely opaque, and then tell the model to re-render it. So here we'll notice that we no longer are seeing in the torso. We are actually seeing into part of it where I have clipped away the skin previously, but elsewhere, instead of seeing through it, we are seeing the shape of the torso itself and what the skin might look like. And again, you can see the successive refinement. Now, of course, this program works with any number of different kinds of data sets. Here are just a few to note. Many different modalities of medical data: CT, MRI, PET, SPECT, etc. Seismic data, fluid flow data, electron density data from X-ray crystallography, nuclear reactor core from non-destructive testing, and various other supercomputing applications. Let's just take a look at one of these to give another idea. This is the nuclear reactor core. And we're loading in this new data set from disk. Here we'll note that one cannot see the interior of the data set because it turns out that the density of the containment vessel is the same as the density of the fuel rods, and this points out the value of being able to slice the data set and ray trace. So what I'm going to do is slice into this data set from the side, stripping away that containment vessel. And again from the front here, the top actually. And now I'm going to switch back to the ray tracing mode. And this time we'll see into the interior of the vessel, and already you can see, even at this low resolution pass, the fuel rods here in the center, which were not visible a moment ago. Now, despite the fact that the performance of this is quite reasonable for the amount of work that's being done, what one would really like is to be able to spin this image around at this point, which is obviously impossible because the single rendering takes anywhere from 2 to 6 minutes. So what we've added to the program is a movie making capability where the user can specify, once you have a view that you think is appropriate and your parameters are set correctly, specify an axis of rotation, how many frames you'd like rendered, where to store the frames, and whether to compress them for a movie or not, and then just hit go, and a movie will be generated automatically That movie might take as long as 10 hours, but it's something that can run overnight without user intervention. Let's take a look at what some of those movies look like. These movies were all generated and then compressed using a 2-bit compression algorithm that comes with TAAC-1 software libraries. And the TAAC-1 is capable of decoding the 2-bit compression at frame rates. And so that's how we can fit up to, let's say, 100 frames of movie data into the TAAC's memory. Here we see a rendered movie of the first data set we looked at, the MRI data of a head. I'll turn on the counter so we can see the different frames going by. We can zoom this up. One can step through the different slices, the different images, that is. Change the speed. Take a look at the sloth that we ray traced earlier. We also now have the capability of doing these movies in stereo, again with the use of a stereo shutter. One can see a 3-dimensional movie. Just to give an idea of a completely different kind of data set, this is electron cloud data calculated on a Cray at Scripps Clinic, and then the volumetric data was rendered on the TAAC-1 using VoxView. Here we can see some of the densities of the electron clouds were made fairly transparent, while others were made, the denser regions were made more opaque and a different color. I will load up one more movie here. This was not generated with the volume rendering toolkit, but rather with ART, the advanced rendering toolkit we spoke about earlier. And these images were rendered at 512 squared resolutions. Increase the speed a little of this jet. There's one more program in the volume rendering toolkit called CloudView. This is a point display program. This is, unlike VoxView, this does not render the original volumetric data, but rather requires a surface generation scheme to create a set of points to be displayed by this. The primitive for CloudView is truly a point. That is an XYZ location in space, a grayscale or pseudocolor value, and a normal vector, an XYZ normal vector. Here we can see a surface generated from a CT data set. All air contact surfaces were generated to be a point set. This data set has 400,000 points in it. And notice that there is no explicit surface to this. That is, it is 400,000 independent points, each with its own normal vector. If we zoom the data set up, we can see that it's only points and not, let's say, polygons or patches, and that the points begin to separate and we see holes in the data set. Nonetheless, this is a very interesting way of looking at data. Notice because there's a normal for each point, we can move the light source around. In fact, on every update of this image, what's happening is the TAAC for every motion is transforming all the points, transforming all the normal vectors, and doing a dot product for the lighting calculation.